All right, so we're going to get through as many of these Exam 5 review questions as we can. We went through, looks like A through F, I think, on number 1. So let's do a couple in number 2, and then 3, 4, 5, and then we'll come back to 1. So let's do SnCl5 minus. We're answering exactly the same questions, except when you have a charge, you're not going to be asked for bond dipoles and if the molecule is polar, because it is an ion, not a neutral molecule. All right, so we find tin on the periodic table. So it is in the column that has carbon, and so that is 4 valence electrons. Chlorine has got the halogens. It's in the column 7. We have 5 of them. All right. Then we have an extra electron. Remember, a negative charge means you have an extra electron. If it was a positive charge, we would have lost an electron. So we have 35 and 5. We have 40 valence electrons. All right. Basically, the only difference was counting, but also formal charge later. All right. And so our central atom is Sn. It is bonded to 5 chlorines. We put in 5 bonds. Each bond is 2 electrons. So we subtract 10. And then we have 30 electrons left. And we need exactly 30 electrons to give all chlorines an octet. Note that tin can have more than 8 electrons, and it has 5 bonds and it has 10 electrons, but that is fine. If you had carbon here, this would be a violation of the octet rule. Carbon cannot have 5 bonds. Carbon has a maximum of 4 bonds, octet. All right, so remember, you got hydrogen in row 1, and all it has is the 1s2, as the duet rule. Maximum is 2 electrons. And that means it's always going to have 1 bond for its 2 electrons. Now, when we're in the second row where we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, this has the 2s2 and the 2p6. So it has a maximum of 8 valence electrons. When you're talking about compounds that have N, O, and F, these must have an octet. If you have a compound that has nitrogen, oxygen, or fluorine and it doesn't have an octet, then it is wrong. The nitrogen, oxygen, fluorine, they're very high electronegativities. They must have an octet. Carbon, for you guys, carbon is probably always also going to have an octet. So I'm going to put usually has octet. All right, but you can have a carbon that is a carbocation. A positive carbon does exist, and it has 6 electrons. Now over here, most of these do not have an octet. So most compounds that have lithium, beryllium, boron have less than 8 electrons. All right, so lithium would normally have 2 electrons. Beryllium would normally have 4 electrons. And boron would normally have 6 electrons in the form of 1 bond for lithium, 2 bonds for beryllium, 3 bonds for boron. Now, carbon almost always has 8 electrons because it always has 4 bonds. All right, but you could have 3 bonds to carbon and a positive charge, and that does not violate the octet rule. What violates the octet rule is if you have more than 8. All right. But also you need to know that nitrogen, oxygen, fluorine, all compounds that have those atoms in it, all those will have an octet. All right, so 30 was the perfect number to give everything an octet. And again, it is fine that your 10 here has more than 8 electrons because it is not in the second row. 10 is in 1, 2, 3, 4, row 5. So it could have a lot of bonds. All right, so we do have a negative charge, and we have to see where that negative charge comes from. Now, we saw that chlorine was supposed to bring in 7. Every one of these chlorines, we had to put 6 electrons around it. And it brought in 1 to share with the 10. And so every chlorine brought in the correct number of electrons, the neutral 7 electrons. The 10, in order to get the 5 bonds, brought in 5 electrons. 10 was only supposed to bring in 4 electrons. It's the atom that brought in the extra electron. And so it has the negative charge on the 10. All right, so we see that we have 5 directions, and they're all bonding. 5 bonding, 0 non-bonding. So we have 5 directions total. And so we know that the geometric arrangement is going to be trigonal bipyramidal. We know the hybrid orbital is sp3d. All right, so now we have to draw it in 3 dimensions. So again, you have to know how to draw a trigonal bipyramidal. You have your axial up, your axial down, and then you have your 3 equatorials in the middle. And since they're all bonds, you just simply put chlorines at each of these sites. And anytime you have 0 lone pairs on your central atom, your molecular geometry will be exactly the same as your geometric arrangement. So the molecular geometry, and I like to put the negative right there on the 10, molecular geometry is also trigonal bipyramidal. All right, and so we do not do any bond dipoles, but we do bond angles, which are 90, 180, and 120. So the 90 is here, the 180 is here, and then the 120 is the ones on the equatorial position. All right, so there's no bond dipole, there's no molecular dipoles when you have charged, you have ions that we are doing. All right, let's go to number 3. Number 3, give resonance structures, resonance hybrid, NO bond order. So we're going to do NO3 minus, and we're going to do NO2 minus. We're going to do the resonance structures for each of these. So the nitrate and the nitrite. All right, so we have to add up our valence electrons. For nitrogen is in column 5, oxygen is in column 6. We have a negative charge. We have to add 1. Nitrogen, column 5, oxygen in column 6. We have an extra electron. All right, so we have 18, 19, 24 here. We have 12 and 6. We have 18 here. So you add up your valence electrons. And in both of these, the central atom is nitrogen. So nitrogen here is bonded to 3 oxygens. So nitrogen is bonded to an oxygen, is bonded to an oxygen, is bonded to an oxygen. Over here, your nitrogen is bonded to an oxygen and is bonded to an oxygen. All right, so over here where we had our 3 oxygens, we had to put in 3 bonds, so we have to subtract 6. And so we have 18 electrons left. All right, each oxygen needs 6 electrons. That's already 18. And the nitrogen also needs a pair of electrons. We need 20. All right, so if you have too many, you put them on the central atom. If you do not have enough, then you have to put in a pi bond for every 2 electrons short. So we're 2 electrons short, and so we need to put in a pi bond. And that's why we have resonance, because do we put the pi bond here or here or here? And the answer is yes to all of those. We have to put one here. Then we draw our resonance arrows. And then we put one here. And then we draw our resonance arrows. And then we put one here. Correct. Yes. All right, so we put in our pi bond and we had 18 electrons. All right, so we have to subtract 2 for our pi bond. Now we only have 16 electrons. We know that's going to be right because we were 2 electrons short. That meant we needed a pi bond. All right, but we can confirm that we need 16 electrons to give everything an octet. Note, nitrogen already has an octet. It's got the 4 bonds to it. But this oxygen needs 4. This one needs 6. And this one needs 6. And when you add those up, you get exactly 16 electrons, and that is the structure. All right, now oxygen is supposed to have 2 bonds and 2 electron pairs to be neutral. Only one of these oxygens looks like it would normally look. The other 2 do not. And so if it doesn't look like it's normally supposed to look, that means it's going to have a charge. All right, so again, oxygen, 6. This oxygen on the left here, it brought in 6. Brought in these 2, and these 2 that it paired up with the nitrogen. So that's why 2 bonds and 2 lone pairs is neutral, because that is 6 electrons that oxygen brought in. This oxygen up here, it brought in these 6 plus this one to share with the nitrogen. It brought in 7. It was only supposed to bring in 6. That has a negative charge. That's exactly the same for this oxygen down here. 6 and then 1 to share with the nitrogen. It brought in 7. And so you have a negative charge for this oxygen as well. All right, now the nitrogen was supposed to bring in 5, but this one only brought in 4. All right, so the 4 electrons that nitrogen brought in, it was supposed to bring in 5. It brought in 1 less electron, and it has a formal charge of plus. All right, and so once we have that set, we know that the double bond to O is neutral, single bond to O is minus, single bond to O is minus, and the nitrogen with 4 bonds is plus. Nitrogen with 4 bonds is plus, single bond negative, single bond negative. And there are your 3 resonance structures for NO3 minus. All right, if we come over to our NO2 minus, all right, so we had our total valence electrons is 18. We only need to put in 2 bonds, so we subtract 4 electrons. We have 14 electrons. Each of the oxygens needs 6. That's 12. But the nitrogen now needs 4. All right, and so that is 16. Again, we need 16 electrons. We only have 14. We are 2 short. Anytime, again, that you are short electrons, you have to put in 2 electrons short. You put in a pi bond. And so the question is, do we put it on this side or the other side? And the answer is yes, we put it on this side and we put it on the other side. All right, so then when we put in our pi bond, we had 14 valence electrons. All right, we put in our pi bond. So now we only have 12 left. And we know that's going to be the perfect number, and we will show it. 1, 2, 3, 4 for that oxygen to give it an octet. 2 for this one, so that's 6. And then 6 more up here makes 12. And so now all of the atoms have an octet. All right, so same thing over here. 6 for this oxygen, 2 for this nitrogen, and 4 for this oxygen. That is your 12 electrons that we had left. And so that is your 2 resonance structures. All right, so again, we can have the same rules we had over there. We know that a 2 bonds to O and 2 lone pairs, that means that this oxygen brought in 6 electrons. That oxygen was supposed to bring in 6 electrons. That means it's neutral. And this nitrogen has a lone pair, that's 2, plus 1 that it brought in for each of these bonds, so that's 2 more, and then 1 for this bond over here. So this nitrogen brought in 5. It was supposed to bring in 5. It is a neutral nitrogen. Regular look for nitrogen is 3 bonds and an electron pair, because that's when it brings in 5. All right, now this oxygen has 6 plus 1 more 7 valence electrons. It was supposed to bring in only 6. That's the negative charge. All right, and so you got your negative charge on your single bond to O. So now we have to do the resonance hybrid, which is just an average. All right, so over here we have N, and then we have an O here, we have an O here, and we have an O here. And this one, N, we have an O here, and we have an O here. Now note that both of these I am writing in the correct 3 dimensions because this one has 3 bonding directions. Remember that a double bond is 1 direction. So this is 3 bonding directions. And so it is a trigonal planar. So I'm drawing it as a trigonal planar. Same thing over here, except this has 3 directions, but 2 of them are bonding and 1 is a lone pair. So the geometric arrangement here is also trigonal planar. All right, because you have 2 bonding directions and 1 lone pair direction. You have a total of 3 directions. So both of these will have a 120-degree bond angle. All right. So now we have to take the average. And so there is some double bond character here, there's some double bond character here, and there's some double bond character here. Same thing over here. We had one where it was a double bond and one where it was a single bond. So you put a little dotted line, a dashed line to show that there is some double bond character for each one of those bonds. We need the average. All right, and so when we do the bond order, all right, so we're going to look at the one here. So bond order here, anytime you have a double bond, the bond order is 2. So I'm going to look at that same one oxygen on the left. Now the bond order is 1. Looking at that NO on the left, NO on the left, the bond order is 1. All right, and so you got to take the average. The resonance hybrid means average. And so you're going to take your bond order of 2 plus 1 divided by the 3 numbers that we added up to get that. And we see that our bond order is 4/3, or 1 1/3, or 1.3 repeating. All right, and so that is our NO bond order for the one on the left. If we go to the one to the upper right, it is 1 plus 2 plus 1. Again, that's 4. Yeah. Double bond is 2, single bond is 1. Okay, so no, you divide by the total number that you added up. You added this one plus this one plus this one. You added up 3 numbers. All right, so then you divide by 3 to get the average. So if you're taking an average of 3 numbers, you have 3 numbers, you got to divide by 3. Over here, what are we going to divide by? When we have our bond order of 2 here and our bond order of 1 here, we're just going to divide by 2. We're adding up 2 numbers. So here your bond order is 2 plus 1 divided by the 2 numbers we added up, the 2 different structures. All right, and so here our bond order is 3/2, or 1 1/2. And so bond order of 3/2, or 1.5 versus 4/3, 1.3 repeating, you see that this is a larger number. And so this is a shorter bond and it is stronger. This is a longer bond and it is weaker. All right, just by the bond order. So a double bond is stronger and shorter. A single bond is longer and weaker. All right, so it is the bond order that is higher is shorter and stronger. The bond order that's lower is longer and weaker. All right, so that's our bond order. Now we can do our charge. So the oxygen on the left, again, we're going to focus on the oxygen on the left over here. We have a 0 charge. On the left, we have a -1 charge. On the left, we have a -1 charge. Again, we're adding up 3 numbers. 0 is a number. 0 and -1 and -1. So to get the average of those 3 numbers, you divide by 3. And so each of these oxygens is -2/3. Because you look at the one on the upper right, you got a negative, a neutral, and a negative. lower bottom, a negative, a neutral. Each one of these has two minuses and a zero. And so each one of these is exactly the same as negative 2/3. When you want your average nitrogen, all right, it's +1 here, it's +1 here, it's +1 here. So +1 plus +1 plus +1 divided by 3, that is equal to 1. 3 divided by 3 is 1. And so your nitrogen average charge is a +1. All right, note that the overall is a negative. You have a plus and two minuses. A plus and two minuses gives you a minus. Here's a plus and 3, negative 2/3. And negative 2/3 plus negative 2/3 plus negative 2/3 is negative 2. And so negative 2 plus 1 is negative 1. To get the average charge here, you've got a 1 on the left again, 0, and on the right, you have a negative 1. All right, so you have your negative 1 plus a negative 1 divided by the two structures. All right, so each one of these oxygens is negative 1/2 or negative 0.5. All right, so that is how you do your resonance hybrid. Note that you don't do averages when it comes to hybridizations. So your nitrogen, 3 directions is sp2, it's sp2, it's sp2. All right, so your nitrogen is always going to be sp2, and the nitrogen's over here again, 3 directions, sp2. All right, so the stronger NO bond, that is with the NO2 minus. This is the stronger bond because bond order 1.5 is greater than bond order of 1.3 repeating. The longest is, of course, the 1.3. The lower the bond order, the longer it will be. Single bonds are longer, double bonds are shorter, triple bonds are the shortest. All right, number 4. Number 4, here's the way I like to do number 4. All right, so on the left, we're going to have a B, and on the right, we're going to have a B. So the question is, give the electron configuration of B2. In order to get the electron configuration of B2, you're going to need the electron configuration of B and the electron configuration of B, and then you bring them to the middle. This B is going to combine with that B, and then we're going to have B2. All right, and so this is an atom. That is an atom. Those two atoms are going to come together and make a diatomic molecule. All right, and so we need boron. So we look at the periodic table. Boron's electron configuration. Boron has 5 total electrons. And so that's a 1s2, 2s2, 2p1. So you have to be able to write the electron configuration for boron. Then you put it in. It is 1s2, 2s2, 2p1. It is 1s2, 2s2, 2p1. All right, and so then you bring them together. Now, there you have to remember that now we're doing a molecular electron configuration. So this is not called the 1s anymore. It is called the sigma 1s, and it will have 2 electrons in it. Then the next one up is the sigma 1s star, meaning anti-bonding. All right, and so then this one, these come together to go down here in the sigma 2s, and then to go up here in the sigma 2s star. All right, then the book puts these as the same. I do not like that. Pi 2py is what I'll call it, and pi 2pz. If you just call it pi 2p, I don't care. That's what the book does. I like it as the pi 2py and the pi 2pz. All right, and this is the sigma 2px. I don't need that high up because I only have 2 electrons, and you have to follow the bus seat rule, Hund's rule. 1 electron goes here, 1 electron goes here. We don't pair them up until we have to. All right, and so the electron configuration of B2 is sigma 1s that has 2 electrons in it, the sigma 2s, or sigma 1s star that has 2 electrons in it, the sigma 2s with 2 electrons in it, the sigma 2s star with 2 electrons in it. And then if you're writing out the electron configuration this way, you have to put a pi 2p. I don't care if you put a y or not, but it has to be a 1. And then you have to have a pi 2p again, but I'm going to put z and it has to be a 1. If you put a pi 2p2, I will not know if you want those to be paired up or not. They are not paired up. 1 is in that orbital, 1 is in that orbital. So this one has 2 unpaired electrons, or I will ask that specifically. And so if you put a 2 there, it's going to look like there are no unpaired electrons. That is wrong. There are 2 unpaired electrons. It is paramagnetic. All right, and so it will be attracted to a magnetic field. The bond order. So when you do the bond order, you take the bonding minus the anti-bonding. And then again, you need to divide by 2 because every bond requires 2 electrons. So you just add up the bonding. That just means the electrons that don't have a star with them. So here's 2 bonding, here's 2 bonding. Both of these are bonding electrons. So when you do the bond order here, it is 2 plus 2 plus 1 plus 1. You have 6 bonding electrons. The anti-bonding electrons are the electrons that are in the stars. That's what the star indicates. So when you see star, that equals anti-bonding. All right, and so there are 2 electrons in that anti-bonding orbital. There's 2 electrons in that anti-bonding orbital, and so there are 4. And again, to get a bond, you have to divide by 2 because there's 2 electrons per bond. All right, and so the bond order is 1. All right, so I do it a different way, but that way is fine. I see that I have 2 electrons down here. That's a bond, and I have an antibond. A bond will get subtracted by the antibond, so net is 0. A bond and antibond, again, net is 0. Then I know that a electron is a half a bond and then another half a bond, and my bond order is 1. You do not have to show this. You can. All right. If you want to just say bond, antibond 0, bond, antibond 0, half a bond, I have a bond order of 1, that is fine. If you want to count up all your bonding electrons, and that is 6, antibonding electrons, that is 4, subtract those and divide by 2, that gives you the exact same answer. All right, so then it asks for B2 plus. All right, so that means that I'm going to take an electron out. So I need to remove 1 electron. And so that is simply a sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and pi 2py 1. All right, so I just had to remove the 1 electron. It is plus. That means remove 1 electron. So you just remove the last electron you put in. All right, so then it asks for the bond order. So now you add up your bonding electrons. 2, 4, 5. Now we only have 5 bonding electrons. We still have the same 4 anti-bonding electrons, and to get a bond, we have to divide by 2. So now your bond order is 1/2. So the bond order of B2 plus is 1/2. Then the next question is B2 minus. Minus means I had to add an electron. And so now I have sigma 1s2, and I have a sigma star 1s2. I have a sigma 2s2. I have a sigma star 2s2. I have a pi 2py 2 and a pi 2pz 1. All right, so when I put in an electron, all right, so I use Hund's rule, and now I have to put that electron in here when I add my electron. So my 2py is now a 2 electrons in my 2py. And then I find my bond order. I add up my bonding electrons, 2, 4, 6, 7 bonding electrons. I still have the same 4 anti-bonding electrons, and I divide by 2, and I get a bond order of 3/2. So your bond order here is 3/2. So this B2 plus has the smallest bond order because it is 1/2. B2 was 1, and B2 minus was 1.5. So that has the smallest bond order. Again, the smallest bond order means that is the weakest bond, and it's the longest bond. This bond order of B2 minus being 1.5 is bigger than 1, it's bigger than 1/2. It is the largest bond order, which means it's the strongest bond, and it is the shortest bond. And so when it asks the question, and it asks for para or diamagnetic, all of these are paramagnetic. So you have 1 unpaired electrons, paramagnetic, 1 unpaired electron, paramagnetic. All right, so each of the B2 plus and the B2 minus have 1 unpaired electron, and they're paramagnetic. And then which boron-boron bond is the longest is the question, and that would be the B2 plus. That is the longest. It is the one that has the smallest bond order is the one that's going to be the longest. The one that's going to be the strongest is the one with the largest bond order. So the strongest is the B2 minus. All right, let's go to number 5. Number 5, it gives you a reaction. It says CH plus 2H2 goes to CH3CH3. And it asks for the delta H. All right, so you're going to be given a table in chapter 9, and it's going to be a bond association energy. It's going to be what you're going to do to find delta H for this chapter, because you're going to be given only this data. You can always do products minus reactants like we did in chapter 6, but that information is not going to be given. For this chapter, the information given is going to be the bond breaking energies. All right, so the bond association energies. And so you have to remember to find the delta H in this chapter. It is going to be the breaking minus the making. All right, in order to break, it takes energy to break a bond, and then you get energy back when that bond is formed. All right, and so that's why it is a negative here. Break, endothermic, make, exothermic. So you add up all of the numbers as positive numbers, and you get your breaking number. You add up all your numbers as positive numbers, you get your making number, and you take breaking minus making to get the delta H of the reaction. All right, so in order to get breaking minus making, you have to draw the Lewis structure. So you can't just look at that and get the answer. You have to draw the Lewis structure. All right, and so you have your carbon bonded to an H. That's why it is written as CH. Your carbon is bonded to an H. this carbon is also bonded to an H. All right, and so the easiest way to do this one is to know that your H always has one bond and your carbon always has 4 bonds. In order for that to be the case, you have to put in a triple bond here. There's a bunch of ways that you can do this. All right, so you can do the Lewis structure, count the valence electrons, see that you're 4 short, you need 2 pi bonds. You cannot put a pi bond to an H. H can only have 1 bond. And so you put in your 2 pi bonds, and that makes it a carbon-carbon triple bond. Hydrogen. Again, hydrogen always has 1 bond. What I like to do is I like to write this twice because that's what the 2 means. You have 2 of them. If you write a 2 out in front, I don't care, but don't forget that you're breaking 2 of those bonds. And now you have your CH3. It's written CH3 because the C on the left is bonded to 3 H's, and the C on the right is bonded to 3 H's. So then you have to determine how many bonds go between the carbons. And of course, carbon has 4 bonds, so it only needs 1 more. All right, so in order to get this problem correct, you have to be able to draw the Lewis structures. If you cannot draw Lewis structures, this is going to be a horrible test. All right, Lewis structures is 90%. I don't know if it's that high, but it's a very high percent of what is required for this test. All right, so then you just make your list of what you're going to break. You're going to break 2 CH bonds. You're going to break a carbon-carbon triple bond. And you're going to break 2 H bonds. All right, so that's breaking everything. We got to break this triple bond. We got to break these 2 CH bonds. And we got to break these 2 hydrogen bonds. And then we have to make a list of what we're going to make. So what we're going to make is 6 CH bonds, and we're going to make a carbon-carbon single bond. All right, so then you just go to your chart and you get your numbers. This one is 411, this one is 836, and this one is 386. This one is 411. This one is... this one is, we're going to call this one 400. That is not right. All right, so I'm just making up numbers because I don't have my chart. So you're going to have the chart. You're going to look up the numbers. All right, and so, well, I'm just going to say I don't know what that one is, and I don't know what that one is, and I'm not really sure about those 2 numbers either. I am sure about the 411. I know a CH bond is 411. But anyway, you're just going to add these numbers up. You're going to get the total. You're going to add these numbers up. You're going to get the total. You get a periodic table. You get a table with all these numbers on it. You get a calculator. And then you take your breaking number, subtract your making number, and that is your delta H. All right, so you'll have to look these up. I know the 411 is right. I know that the triple bond is 800 and something. I'm guessing 36. Hydrogen, not real sure about that 386. And I know that carbon is not 400. I was just making up a number, but probably not a good idea. All right, so just look those up on your chart, get your totals, subtract them, and you're going to get a delta H that is going to be negative 200 and something. And so then that is going to be, of course, an exothermic reaction. All right. So again, you have the hard part of this one is determining what are you going to break. You break everything on the left side. You're going to break all of the reactants. And then you're going to make everything on this side. You're going to break it. Everything on this side, you're going to make it on this side. And then you have your chart. You look up your numbers for all these bonds. Add up your breaks, add up your makes, and it is breaking minus making. And the reason why it's breaking minus making, endothermic to break, exothermic to make. So that's where the negative comes in. Exothermic to make it. Get energy back. All right, number 6. Number 6 is just radius. All right, so you have S minus 2 on the periodic table. You have O minus 2. Remember, F is the smallest. So when you're talking about radius, it's going to decrease to your fluorine. All right, and so your radius is decreasing as you go up a column. I wrote it this way because that is where it's at on your periodic table. All right, so which one has the largest radius? Well, the largest radius would be the S minus 2. When you're looking at O minus 2 versus Mg plus 2, these are isoelectronic. And if you don't know what isoelectronic is, well, you're going to miss some easy questions. Iso means same, electrons. Right? So same electrons. All right, so you look at the periodic table, oxygen has 8 protons, but it has an overall minus 2, which means it has 10 electrons. You look at magnesium, it has 12 protons. On the periodic table, it is atomic number 12, but it only has 10 electrons to give an overall plus 2. So isoelectronic just means you have the same number of electrons. Anytime you have a charge difference, the one that is more negative is the largest. Always the more negative. Or you can look at it as less positive. All right, so if they're both positive, the one that's less positive is the largest. So your O minus 2 is much larger than your Mg plus 2. All right, so let's go back up to number 1. Again, question number 1 and 2, those are over half of the test is questions about number 1 and 2. All right, so we're on G, which is argon, Cl2. Argon is a noble gas. It is in column number 8. Chlorine is the halogens, column number 7. All right, and so you've got your 14 plus your 8. All right, so you got your 22 valence electrons. Argon is the central atom, bonded to a chlorine, so we subtract 4. 18 electrons is what we have left. All right, to give everything an octet, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We need 16 electrons to give everything an octet. That means we have 2 extra electrons. All right, so again, when we did the ones with the resonance structures, we were short 2 electrons and you had to put in pi bonds. When you have extra electrons, you have to put them on the central atom. All right, and so you put the 2 extra electrons on central atom. All right, so then we do our directions. We have 2 bonding directions. And we have 3 non-bonding. And so that is 5 directions. And so our geometric arrangement is trigonal bipyramidal, hybrid orbital, sp3d. All right, so then we have to draw in 3 dimensions. So you have to be able to draw a trigonal bipyramidal. So that is axial up and down, and then the 3 equatorials. And then you have to know that you're putting your electron pairs in the equatorial position. And so all lone pairs on a trigonal bipyramidal will go in the equatorial position. And then you have your Cl, then you have your Cl. All right, and so you then have your molecular geometry, and you see that all you can see is the chlorine on top and the chlorine on bottom and the argon in the middle. So this is linear, straight line. And now the bond angle is 180. All right, so the chlorine was there and there. All right, electron pairs around your central atom in the equatorial position. All right, and so then we do our bond dipoles. All right, so chlorine is higher electronegativity. Again, if I don't care which way you draw the arrow here. Fluorine is the most electronegative. So since fluorine is the most electronegative, it increases as you go up and increases as you go this way. Now, note that neon is over here. All right, and so since fluorine is the highest, that means that fluorine is higher than neon. And since argon is here, that means that chlorine is higher than argon. So, but if you went with the trends and you said to the right increases, and so you're going to say argon is a higher electronegativity, I really don't care in this case. So that is not important. What is important is that whichever way you're pointing your arrow, the arrow points and you have to have the delta minus. All right, so the arrow is showing the movement of electrons in that bond towards the chlorine, which means it's delta minus. If you're doing it the other way, then fine, but then your chlorine is delta plus and your argon is delta minus. And since this is a noble gas, I don't care which way you would do that. And then again, your electron pairs, again, very close to the argon, so barely moving out the electrons. They are right connected to the argon. They're not a bond distance away. They are right next to it. All right, and so you see that your center of delta minus is exactly on the argon. So your delta plus is on the argon, your delta minus is on the argon. This is nonpolar. The average minus is right on the argon. The plus is right on the argon. This is nonpolar. Dipole moment is 0, which you will get in every time that you get a linear and the two things are the same. So this is chlorine, this is chlorine. If one was chlorine, one was fluorine, well, then it would not be exactly the same because fluorine would pull out more electrons than the chlorine. But when they are the same and it's linear, the same atom that's linear, it's going to be nonpolar every time. All right, next one was XeF4. That is H. All right, so now we have 8, and then we have 7 times 4. So we had our 28 and 8. We have our 36 valence electrons. Central atom is Xe, bonded to 4 Fs. So we subtract 8, and we have 28. And what do we need to give an octet? Well, each one of these fluorines needs 6 electrons. So that's 24. So we only need 24 electrons. We have 4 extra because the Xe already had the 4 bonds and it already had its octet. Again, when you have extra electrons, you put them on the central atom. If you don't have enough electrons, every 2 electrons short, you have to put in a pi bond. Too many electrons, you just put them on the central atom. All right. And so now we look at our number of directions. You got 4 bonds. You got 2 lone pairs. You have 6 directions. And so your geometric arrangement is octahedral. Your hybrid orbital is sp3d2. You have 6 directions. You need the 6 orbitals, 1 s, 3 p's, and 2 d's. Right? And now we have to draw it in 3 dimensions. So you have to be able to draw an octahedral. All right, now I always put my first lone pair on the bottom. That is just where I put it. It makes no difference where you put your first lone pair. Now the second lone pair makes a huge difference. Wherever you put the first lone pair, the second lone pair has to go 180 degrees away, as far apart as possible. So if you put one coming out on the left, it's got to go back on the right. So I recommend up and down, but it doesn't matter. As long as they're 180 degrees away, that is the same structure. All right. I always start my octahedral by putting the lone pair on the bottom. If I have one, that's where it goes. If I have two, well, then the other one goes opposite. If you have three, then again, your choice. All four of those positions are the same after you put in those two. All right, and so here is your three-dimensional structure of XeF4. All right, and so now you have a molecular geometry of square planar. And a bond angle of 90 and 180. And so now we do our bond dipole. So F is nice. We know F is the largest electronegativity. You always point to the F's, and you always put delta minus by each of your F's. All right, again, the electron pairs will be pulling out electrons, but very slightly because they are right next to the Xe. They are not a bond distance away. They are right next to it. All right, so we see that the Xe is the delta plus. Then we have to find the center of delta minus. So you got your minuses here, center is Xe. Minuses here, center is Xe. And your minuses there on the lone pairs. This is completely symmetrical where all the negatives end up right on the Xe. So again, this one is non-polar because the center of delta plus and delta minus is right on the Xe. You have a dipole moment of 0. Formal charge, there isn't one, but why isn't there one? Well, F always has one bond and 6 electrons. That's the 7 it brought in. But Xe, all right, so it has 4 electrons for the lone pairs, and then it has 4 electrons for sharing with the F's. So the Xe also brought in 8 like it was supposed to. All right, I is interesting. I can be asked in a couple of different ways. This one just says, give the answers, and it doesn't say anything else. I guess I'll do it both ways. All right, so aluminum is in column 3, and then chlorine is in column 7. So you have 24 valence electrons. Central atom is aluminum, bonded to 3 chlorines. So we subtract 6 and we have 18 electrons. Now, here's where the trouble comes in. 18 electrons is not enough to give everything an octet. But note that aluminum is in the 3rd row. So you had your lithium, beryllium, and your boron, and aluminum is right below boron. So lithium has 1 bond, beryllium has 2 bonds, and boron has 3 bonds. And same with the aluminum. So if there is no other instruction, this is a fine answer. All right, and so this would be your structure. If the question said all atoms must have an octet, then you would have to see that the aluminum would need 2 electrons for an octet, and you would be 2 electrons short. All right, so this one and all the answers will be exactly the same, regardless of the way you do it. All right, so you could say that you're 2 short, and so then you have to put in a pi bond. So then you got your Cl, and your Cl, and you got to put in a pi bond. Well, this could be a resonance question because you could put the double bond in here, you could put the double bond in here, or you could put the double bond here. All right, and so then when you subtract the 2 electrons for the pi bond, you would have 16, and 16 is the perfect number to give all of the atoms an octet. All right, and so this would be then your 3 resonance structures. So it definitely could be, here is the question, everything must have an octet, because then I would say, all right, up here, where everything's a single bond, aluminum was supposed to bring in 3 electrons. It brought in 3 electrons. It is neutral. Chlorine was supposed to bring in 7. It brought in 7. Neutral. So that is all neutral. So this could be done for 2 reasons. One could be, I want to know if you can do formal charges. Or it could be, I want to know if you can do the resonance structures. All right, so there's the 3 resonance structures. Now for doing the charges, all right, so 2 of our chlorines are just like they're supposed to be with the 7 electrons. All right, but this chlorine is not the typical chlorine. This chlorine only brought in 6 electrons. It was supposed to bring in 7. This chlorine has a positive charge. The aluminum was supposed to bring in 3 electrons. In this structure, the aluminum brought in 4 electrons, and it is negative. So every aluminum here is minus, and every double bond to chlorine is positive. And so you have your formal charges. All right. But again, it doesn't matter if you look at any of these, they all have 3 directions. 3 bonding directions, 0 lone pairs. All right, and so your geometric arrangement is going to be trigonal planar. And your hybrid orbital is sp2. Then you draw it in 3 dimensions. It's already drawn in 3 dimensions because it's planar. All right, so if you want to write it out so that you show it is as close to a 120-degree bond angle as possible. All right, so molecular geometry, since there's no lone pairs, it is still trigonal planar. Your bond angles are 120. Then your dipoles. So you would go out to the aluminum, to the aluminum, to the aluminum, or to the chlorines. They're all minus. They're all higher. All right, and so you see that this is completely symmetrical. And so everything that is symmetrical is going to have a dipole moment of 0. This is non-polar. So this is a non-polar, perfectly symmetrical molecule. All right, J is O3, so that's 18. O minus 4, and so you have 3 O's. So you're going to have 2 bonds, and you have 14 electrons. Now here is where you have no choice. If you add them up, you got 2, 4, 6, 8, 10, 12, 14, 16. We need 16. All right, so the only ones that must have an octet are the ones that states in the problem that it has to have an octet, or nitrogen, oxygen, and fluorine. All right, these must have an octet. If you give any structure where nitrogen, oxygen, and fluorine does not have an octet, it is the wrong answer. Every nitrogen, every oxygen, every fluorine must have an octet. And so this one must have a pi bond put in. All right, so again, you can put it there, or you can put it there. You got it in 2 different spots. All right, and so then we're down to 12 electrons, and that is the perfect number to give all of your oxygens an octet. And only one of these oxygens looks like it's supposed to look, and it's this one here where you have your 2 bonds to oxygen, because that's the one that brought in the 6 electrons. The one in the middle only brought in 5. So it is a plus charge. The one on the right brought in 7. It is a minus charge. All right, so O3 minus would be a good problem as well, or O3 ozone would be a good problem as well in order to get your Lewis structures and your formal charges down. All right, so, okay, this one's minus, and this is plus. All right, but it didn't ask for resonance structures. It only asked for the geometric arrangement. So you have 2 bonding directions. Remember that a double bond is 1 direction. 2 bonding directions, 1 lone pair. So you have 3 directions. So again, we have our trigonal planar. And then you have your hybrid orbital as sp2. Then you have to draw it in 3 dimensions. So you have your central O, and then we're going to draw a trigonal planar. All right, and so then our molecular geometry is bent. And the bond angle is 120. Remember, your bent, it can be from trigonal planar, which has a bond angle of 120, or you could get bent from tetrahedral when the bond angle then is 109.5. So the bond angle comes from your geometric arrangement. All right. And then polar or non-polar. All right. So you have anytime your central atom has 1 electron pair, you have a polar molecule. Here is where you would have to say, well, there's no electronegativity difference, and you are right. So now you have to look at the resonance hybrid. Your resonance hybrid looks like this, where your bond order is 3 halves, and then your charge. The oxygen in the middle is positive. The oxygen at each end is -1/2, -1/2. All right, so your center of negative is between the 2 oxygens at the bottom. Here is the center of minus, and there is the center of plus. And so there is a separation between the center of plus, which is a formal charge +1 oxygen, and the center of minus, which is the formal charge -1/2, the center here. There's no bond dipole to draw because oxygen's electronegativity is exactly the same as oxygen's electronegativity. So here's a case where you have, normally it's opposite. So here you have a bond that is a non-polar bond, but the molecule that is a polar molecule. Normally it's the other way around where you have very polar bonds, but they are all very symmetrical and the molecule is non-polar. So this one is very different. All right, and so this one is polar. All right, CO2. All right, so now when I go to CO2, this is one where I would do fast. I have my central atom is carbon. I know carbon has 4 bonds. I know oxygen has 2 bonds. You can count all the electrons if you want, but I would highly recommend knowing that carbon has 4 bonds and oxygen has 2 bonds. All right, and so I go right to the answer, but you can do it correctly. Here's 4 plus 12 is 16. You put in your 2 bonds, that was -4. You put in 12. You needed 16. That means we need to add 2 pi bonds. And so you put a double bond on each side, and you have your CO2. All right, so directions. You have 2 bonding directions. You have 0 lone pair directions on the central atom. So you have 2 directions. So your geometric arrangement is linear. Your hybrid orbital is sp. Molecular geometry is linear. Again, the same because you have 0 lone pairs. And then your bond angle is 180 degrees. Oxygen is more electronegative. So each oxygen is delta minus, and the carbon is delta plus. The center of the minus is right on top of that carbon. And so this is non-polar. L is interesting. All right, so L is Cl2, F2. All right, so we have carbon. That's 4. And we have 7 times 2 for the fluorine. We have 7 times 2 for the fluorine. And so that is 32. Valence electrons. Central atom is carbon. Carbon is bonded to a chlorine, a chlorine, a fluorine, and a fluorine. So we subtract 8. We have 24. That is the perfect number to give everything an octet. All right, and so we have 4 directions. all of those are bonding directions. All right, and so we have our geometric arrangement is tetrahedral, and then our hybrid orbital is sp3. Then we have to draw a tetrahedral. Tetrahedral, all spots are exactly the same. It doesn't matter where you put the two F's. You cannot put them in the wrong place. It doesn't matter where you put the two chlorines. You cannot put them in the wrong place. All spots in a tetrahedral are exactly the same. All right, so this is where, so then our molecular geometry is tetrahedral because there's 0 lone pairs, and then the bond angle is 109.5. All right, so now we have to do our bond dipoles. So this is where it gets interesting because you have your fluorines that are more electronegative than carbon. You got your chlorines that are more electronegative than carbon. Because chlorine, we know the number, it's 3.2. Carbon, we know the number, it's 2.5. Fluorine, we know the number, it's 4.0. All right, and so the fluorine is delta minus. The chlorine is delta minus. The chlorine is delta minus. All right, so note that I wrote a smaller looking delta minus for the chlorine because that bond is not as polar. This bond has a difference of 0.7. This bond has a difference of 1.5. All right, and so the fluorine bond is much more polar than the carbon-chlorine bond. And so when you look at your delta plus right there on the carbon, and then you see that it's surrounded by delta minuses, you might think that that center of delta minus is right on the carbon. It is not, because the fluorine is pulling out a lot more electrons than the chlorine is pulling out. And so your center of delta minus is going to be closer to the middle of your two fluorines. All right, and so your polar molecule goes this way. So this is a polar molecule. If this was CCl4, then it would be nonpolar. If it was CF4, it would be nonpolar. But when you have a mixture of chlorines and fluorines, now you're not completely symmetrical because fluorine is going to pull out more, it's going to be more polar, it's going to pull out more electron density than a carbon-chlorine bond would pull out. All right, let's do N, and that will be the last one. N, it's HNO3. This is an oxy acid. When you have an oxy acid, that means you have oxygen, and it starts with H. That makes it an oxy acid. For an oxy acid, you have to know that the H is bonded to an O. Anytime you have an oxy acid, the H has to be bonded to the O. And H is never the central atom. So N is the central atom. It's bonded to 3 O's, and one of those O's is bonded to an H. All right, and so we add them up. 1 plus 5 plus 18 is 24. We just put in 1, 2, 3, 4 bonds. We subtract 8. And so we have 16 electrons. 2, 4, 6, 12, 13, 14, 15, 16, 17, 18. We need 18. So you have to put in a pi bond. And here you have to know that oxygen wants to have 2 bonds. You cannot put a pi bond here because then that would give oxygen 3 bonds. And so here you would put it in the place that gives the fewest formal charges. And so this is the structure of your nitric acid. And then the formal charge, the nitrogen only brought in 4, this oxygen brought in 7. And so you have your formal charges for your nitric acid. And so this is trigonal planar, sp2. Since there's no lone pairs, it's trigonal planar. And that is a 120-degree bond angle. And it is polar. All of your acids will be polar. All right. And that is it for today.